Hello, everyone. Sorry for not being there. I would like to be there in person, but unfortunately I couldn't do that. So I'm here to present the DNS of intrinsic unstable fluid flames using deficient reactant thermochemistry. I'm presenting the validation and scaling using NiCoRS. As you know, lately hydrogen become really popular fuel, and everyone talks about hydrogen to use hydrogen because it can help us to reduce the carbon. And for that reason, now hydrogen is one of the important candidates for using as a carbon-free fuel. So still there are challenges using hydrogen. Burning it is still has some difficulties, storage and other problem of transportation and other stuff. But here I'm going to talk about the intrinsic flame instabilities because as you may know, we have two types of intrinsic instabilities inside the hydrogen flame. One is Dario-Lambda mechanism, and the other one is thermodiffusive mechanism. Dario-Lambda instabilities are mostly related to large-scale effects due to thermal expansion across the flame, and the thermodiffusive instabilities are small-scale effect due to diffusion of the hydrogen. And these instabilities Lewis-dominated phenomena. And here in this picture, you can see if we have a Lewis number higher than Lewis critical because of the Markov length, we'll have more diffusion and the flame for Lewis higher than Lewis critical, we have a stable flame, but if we have the Lewis less than Lewis critical, the flame becomes unstable. And if we want to talk about the length scales of intrinsic instabilities, we can take a look at the dispersion relation. In dispersion relation, we have in here you can see in this chart we have the growth rate of each wave number inside the flame. When we calculate this the dispersion relation using DNS, you can see here we have two parameters. The first one is the is related to hydrodynamic mechanism because this parameter, if you take a look, this K here is positive. So as the wave number becomes higher, so the growth rate becomes higher. And in this chart, we can take a look at two different types of phenomena. One is stabilizing and the other one is stabilizing. When the growth rate is increasing during the time, so it makes the flame unstable. So this is the case. Or if we reduce the growth rate during the time and as the flame evolves, we have the stabilizing effect. So for that reason, here you can see in this chart, the first one is related to Dario-Lambda instability, and the second one, which has the power of 2, it's a thermodiffusive mechanism. As here you can see, it is related to Markov length, and it's related to a Lewis number. So for the stabilizing case, which is the case as the Lewis number is less than Lewis critical, which is the case for hydrogen flame. So for that reason, it's really important for us to take a look at these instabilities inside the hydrogen flames. Also, the other thing that we can, the parameter that I will use that later on is this NC is the number of unstable wavelength inside the domain and how much unstable wavelength you put inside your simulation and it is somehow represent how big your flame is. So if I want to just say orally, the high Karlovitz effect are related to small scale effects. And on the other hand, the large scale effects that we are interested in are the cases that going for bigger flame and using a lot of unsettled wavelength inside the flame domain and the flame domain. So for that reason, we needed a large simulation and going to big simulation to capture these effects inside the domain. And that was the reason we have to go for using GPUs and NEC-RS. But our approach was going for deficient reactant approach. We use a low MAC formulation, and for the reaction part and reactant part, we use a one-step irreversible reaction rate, which uses the Arrhenius reaction. And for that reason, we only have one variable or one in somehow one fuel. For that reason, we can reduce the computational time. And the other advantage is that we can go for asymptotic hydrodynamic theory for premixed flame to compare the results and compare with the asymptotic theory. Before, we had implemented this method inside the NEC 5000, and we had a 2D dataset in NEC 5000. In this dataset, we had also diurnal unstable flame and thermodiffusive unstable flame, which you can see only the thermodiffusive part. This has three different flames, which are named TD1, TD2, and TD3. And as the number grows, the flame gets bigger. The TD1 has a 40 flame thickness inside the domain, or 7.6 unstable wavelength inside the domain. And TD2 has around 100.05 flame thickness, and TD3 has 400 flame thickness inside the domain. So for that reason, we decided to migrate our code from CPU to GPUs to be able to use these big system and going for really large simulation. And because, this dataset was 2D and going to 3D will get the simulation much larger, and we needed to be able to go for really large simulations. For first step, we started to validate the code and going from NEC 5000 to NEC-RS. And at the first step, we decided a reference solution of 1D flame in NEC 5000 and simulated and that using NEC-RS. For the first step, we use, as you know, NEC-RS uses OCA language, which enables you to use CPU or GPU or accelerators as a backend. So as the first step, we went to the CPU backend, which doesn't make any difference. It's somehow this language transport the code to the backend, which can be CPUs or CPUs. So at the first step, we went for CPUs, and here you can see good agreement between NEC 5000 and NEC-RS for two different polynomial order of 7 and 9. And after that, we compared the one of the CPU solution with the GPU backend, and again we had the good agreement between the results. So we can ensure that the code is working well, and we can go for 3D simulation inside the NEC-RS. For that reason, we have done the TD1, which is the smallest one, and TD2 lately in Jülich Supercomputer Center, and now we are not sure that if we can go for TD3 because that will get really big. Now you can see the size of TD2. So the TD1 was this case, which had around 7.6 unstable wavelength inside the each direction, and it used 1 million spectral elements, which is around 300 50 million grid points inside the domain. And here you can see the isosurface of the constant deficient reactant, which is colored by the temperature. And you can see the flame surface. Also here we compared the 2D versus 3D slices. And the idea is that to compare the 2D flames versus 3D and take into account the third and the extra direction of the 3D flame. The bigger one was the TD2, which here you can see a snapshot of the flame. Again, this simulation had around 18 million spectral element, which is around 6.3 billion grid points totally. And for that reason, this is a really big simulation. And again, we compared the slice inside the 3D flame, and we had the higher temperature inside the fingers, flame fingers, and that's for the extra dimension that we have and the diffusion that comes from the extra dimension. For this case, we have done the scaling to be sure how many nodes, how many ampere ranks is the best for doing the simulation, because it's a really big simulation. For this reason, we use the Joules booster, and here you can see that we have 520 as a start point, because we needed to feed the RAM, the memory of the GPUs, and we needed at least 130 nodes each. So we went up to 920 ampere ranks, and here you can see a good agreement and good scale and liberty between the real case versus the ideal line. And if we go upper, you can see that it will diverge, and it's not really suitable for that. And the only part of the results that I'm going to compare here is the consumption speed between 2D and 3D cases. Is that in 2D, as the flame gets bigger, you can see here we have a big jump between TD1 and TD2, and between TD2 and TD3, there is not that much difference in consumption speed. But when we go for 3D flames, which are these red squares, you can see even for the smaller case, we have much higher consumption speed compared to the 2D one. And that's the reason that maybe it's better to go for 3D cases. And as we increase the size of the flame and go to TD2, you can see we don't have these big jump here. And so we can expect that the TD3 also don't have that much big or higher consumption speed. And the other thing that is the reaction rate analysis is that if we plot the PDF of the reaction rate, you can see in 2D, and they are the same, and we have a peak here around 3. But the 3D case, we have a higher reaction rate because of, again, that extra dimension that we have. And for that reason, 3D cases has a wider reaction rate, and they are consuming more fuel compared to 2D simulation. So maybe it's time to go always for 3D simulation and DNS, as we have more resources in supercomputing centers, and that seems and that's the one of the conclusion that I can have between 2D and 3D flames. Okay, I would like to thank you, the BSc and also JSC, for helping us for doing this simulation. And thank you all. And sorry again that I'm not there in person. Any question, and I would be there.